Hello. Hello and welcome to this video. In this video, we will solve 10 more problems of uh, curious equations and quadratic equations. We have solved till problem number 140. So we will solve 10 more problems. As always, I will say that when I'm stating the problem, you should pause the video. And if you cannot solve the problem, only then look at the solution. So without further ado, let's get started. The question 141 says that if p and q are odd integers, so that the equation x square plus 2px plus 2q is equal to 0 has no rational roots. So we look at the solution. The discriminant would be 4p square minus 8q, that is 2 square root of p square minus 2q. Now p and q both are odd, so p square will be odd and 2q will be even. And therefore, it would be eventually odd. That is, our discriminant is odd. So we assume that it is a perfect square for rational roots. Okay. Yeah. So because if odd number is not a perfect square, then it will become irrational. Okay. Now, so p would be our second term is 2p. So minus 2p plus minus d by 2. So 2p would be what you call, when divided by 2 will become odd. Okay. So the roots would be odd. All right. So if you look at the roots, what would be roots? Minus p plus minus square root of p square minus 2q. So minus t would be odd and p square minus 2q is odd. So we let the roots to be r. Okay. All right. So p square minus r square is equal to 2q. If you let this term to be r, then p square minus 2q is equal to r. So p square minus r square is equal to 2q. Now, if p is odd and r is odd, okay, then the squares would be odd, which we have shown here. And we evaluate this, then 2m plus 2n plus 2 into m minus n is equal to q. Now, this is an even term, and this may be odd or may be even, okay? But this is even, so q has to be even. Therefore, there is a contradiction, okay? So, our assumption that D would be a perfect square would be incorrect. That is, D cannot be a perfect square, so we don't have rational roots. Okay, now we solve question number 142. Show that there cannot exist an integer n such that n cube minus n plus 3 divides n cube plus n square plus n plus 2. So we let that there is some n for which it is possible. Okay. So the GCD of the two given terms would be n cube minus n plus 3. Now we use the Euclidean algorithm and we compute the GCD. So the first term when divided by n cube minus n plus 2, it would give n square plus 2n minus 1, which would further give minus 2n square plus 3, which would further give 4n plus 5, which would further give 4n plus 5, which would further become 3n minus 4, and which will eventually become n plus 9, minus 31 comma n plus 9. So this will belong in the set of plus minus 1 and plus minus 31. Okay. So we have 4 possible values of this for n cube minus n plus 2. That is plus 1, plus minus 1 and plus minus 31. But if you put in these values, you will see that the division is not possible. Now we solve question number 143. if Sn is equal to 1 plus q square up to q to the power n, and this is small s, and capital Sn is equal to 1 plus q by 2 plus 1 plus q whole square by 2, and so on up to 1 plus q by 2 to the power n, then prove that this is choosing symbol. This is the combination of choosing 1 out of n plus 1. This is the combination of choosing 2 out of n plus 1 into f, and so on, is equal to 2 to the power n Sn. Now, to understand this problem solution, you need to be familiar with how permutation combination works. So if you don't know how permutation combination works, you can skip this problem and come back later. So we look at the solution. Okay. So small Sn is equal to q n plus 1 minus 1 by q minus 1, because it is 1 plus q square. It's a geometric progression. And similarly, capital Sn is equal to 1 plus q by 2 whole to the power n plus 1 minus 1 by 1 plus q minus 1 by 2. So this is equal to 1 plus q to the power n plus 1 minus 2 to the power n plus 1 divided by 2 to the power n q minus 1. And therefore, 2 to the power n Sn is equal to 1 plus q to the power n plus 1 minus 2 to the power n plus 1 by q minus 1. Now, the general term of the left hand side of this expression is C combination of R with from n plus 1, combination of R items from n plus 1 items, into q to the power R plus 1 by q minus 1, that is this guy, and minus combination of R items out of n plus 1 into 1 by q minus 1. So we simply substitute this in the TR and we get. So we find the sum of these two, and we find the sum to be 1 by q minus 1, 1 plus q to the power n plus 1, minus 1 minus 2 to the power n plus 1 plus 1, and 1 will get cancelled, and we will have this as the value. Okay. So to understand this, how summation of combination of R items from n plus 1 becomes 2n plus 1 minus 1. So for that, you need to understand the binomial theorem. Without understanding binomial theorem, you will not be able to understand this. And even this one, for this, you have to understand binomial theorem. There is a mistake here. The mistake is that when you take this r to the power q plus 1, it's not a mistake actually, it's accurate. You see, it does not start with 0. So if you know binomial theorem, it has to start with 0. This expression has to start with 0. Since it is not starting with 0, we have to subtract 1 from this. Okay, this is for those students who know binomial theorem. So for example, expand the general term of 1 plus x to the power n is given by combination of r items out of n into x to the power r. So this is that general term, and this is the expansion of 1 plus 1 to the power n. Okay, here both the terms are 1. So 2 to the power n plus 1 is the value, and minus 1 because the first term is missing from both. So that's how we solve 143. Now we look at question number 144. It says that solve for x, y, z the equations a is equal to xy by x plus y, b is equal to yz by y plus z, and c is equal to zx by z plus x, where a, b, c are not 0. So here what we do is we write 1 by a is equal to 1 by x plus 1 by y, 1 by b is equal to 1 by y plus 1 by z, and 1 by c is equal to 1 by x plus 1 by z. Then we find out a minus b by a plus by ab, which is equal to z minus x by xz. 1 by c is equal to z plus x by zx. So from these two, we find that z is equal to 2abc by ab minus bc plus ca, and similarly x is equal to 2abc by ab plus bc minus ca, and y is equal to 2abc by bc plus ca minus ab. So very straightforward problem. Question 145 says that solve and find the non-trivial solutions of the system of equations x square plus xy plus zx equal to 0, y square plus yz plus zx equal to 0, z square plus zx plus zy is equal to 0. So in this, we add all the equations and we get x plus y plus z whole square is equal to 0, which implies that x is equal to 0 by 0. Since x, y, z can assume any value as long as x plus y plus z is equal to 0. So if x is equal to a, y is equal to b, then z is equal to minus a minus b. So that is the solution. Now we solve question number 146. It says that solve x square plus xy plus y square is equal to 7, y square plus yz plus z square is equal to 19, z square plus zx plus x square is equal to 3. So here what we do is we take the second equation, first equation and subtract. We get z square minus x square plus yz minus xy is equal to 12. That is z minus x into x plus y plus z is equal to 12. And similarly, we have y minus z into x plus y plus z is equal to 4. And y minus x into x plus y plus z is equal to 16. So once you have this, we can say that z minus x is equal to 3 into y minus z, and y minus x is equal to 4 into y minus z. That is 3 into y minus x is equal to 4z minus x. So once we have this, we can say that x, y, z is equal to minus 1, 3, 2, or 1 minus 3 minus 2, and these values are the solution of the equation. Question 147 says that determine all solutions to the equation in set of real numbers. X square plus 3x minus 4 to the power cube, 2x square minus 4x plus 3 to the power 3 is equal to 3x square minus 2x minus 1 to the power 3. So we let a is equal to x square plus 3x minus 4 and b is equal to 2x square minus 5x plus 3. So the given equation will be of the form, you observe that this term is sum of these two. Okay. So the given equation will become of the form a cube plus b cube is equal to a plus b whole cube. That is 3ab into a plus b is equal to 0. That implies that either this is equal to 0, or this is equal to 0, or this is equal to 0. Once we have these three equations, we get four roots as minus 4 comma 1, 3 by 2 comma minus 1 by 3. Question 148 says that show that there is no positive integer satisfying the condition n to the power 4 plus 2n cube plus 2n square plus 2n plus 1 is a perfect square. So, okay, all right. So, given term we can write as n square plus 1 into n plus 1 whole square. So, for the given number to be a perfect square, n square plus 1 will have to be a perfect square. Now we see that the perfect squares are 1, 4, 9, 16, etc. That is, the difference between a perfect square is no more than 1. Okay, difference between perfect squares is more than 1, and it is increasing. We have 1 which is a square of 1, then 2 square is equal to 4, 3 square is equal to 9, and 4 square is equal to 16, and 5 square 25. You see the difference is 3, and then 5, then 7, then 9. So the difference is increasing. So we see that it is n square and plus 1. So we can see that n square plus 1 cannot be a perfect square. Now remember that this is for positive integer, that is n has to be positive integer. If n is not positive integer, then there is a possible value of n is equal to 0. But given that n is positive integer, that is n is at least 1, n square 1 cannot be a perfect square. And then the only possible solution is n plus 1 whole square is equal to, which implies that n is equal to 0. So therefore, there is no such positive number. Question 149 says that find the possible solutions of the system of equations a to the power x is equal to x plus y plus z to the power y, a to the power y is equal to x plus y plus z to the power z, and z to the power z is equal to x plus y plus z to the power x. So we see, so we are given that a to the power x by y. So you divide Okay, these two. A to the power x by y is equal to a to the power y by z is equal to a to the power z by x. Not divide actually. We substitute. All right. So once we have this, we can say that x is equal to y is equal to z. That is a is equal to 3x, which implies that xyz is a by 3. Xyz is all of them are a by 3. Question 150 says that so that 2x cube minus 4x square plus x minus 5 cannot be factored into polynomial with integer quotient. So we assume that it can be factored into polynomials with integer coefficients. So it is, if you see this, this is third degree equation. So one such factor should be of the form px plus q. The other could be a quadratic equation. Then from rational loop theorem, we have q is equal to plus minus 1 and plus minus 2. And p is equal to plus minus 1 plus minus 5. But we see that no such value satisfies the given polynomial, and thus px plus q cannot be a factor. So you need to understand rational loop theorem, how we arrived at this value. So with this, we come to the end of this set of problems, and I hope that you have found this video useful and informative. So please subscribe to the channel and like the video so that it can reach many other students like you, because that is how YouTube algorithm works. The more the subscription, the more the like, the more the views, the more the watch time, the more is the reach of the video. And the second thing which happens is that it motivates me to make more such videos. So I hope that your studies are going well and you are doing well in general in life. So thanks a lot for watching the video. Enjoy.